simulation. We have seen the 4 functions. Actually, 4 built-in functions in R: B tag, P tag, R tag, Q tag, to find the probability, cumulative probability, generating random numbers, etc. Now, all those things are possible only for known distributions. All those things are available only for known distributions like binomial, Poisson, exponential, gamma, etc. Suppose you have to generate random numbers from a distribution which is not available in that list. Which is not available in that list. For example, suppose you are getting a function in your research, f of x is equal to something like f of x is equal to something like x cube or x cube. Okay, of course, it is a beta family, but something like this one. No, it is a density function. X cube is positive when x is between 0 and 1. When you integrate this one, x raised to 4 by 4 will come, 4 and 4 will get cancelled, and you will get 1. How to generate random numbers from this distribution? Okay, that is, this is not, suppose this is not available. Actually, this is available. This is a beta family. It's a member of the beta family. So that is available. But suppose you have a density function like this. What is the technique? Okay, we will make use of f of x. We will make use of f of x. What is f of x? Probability that x less than or equal to x. And the minimum value is 0 and the maximum value is 1. There's a theorem. If x is a continuous random variable, f of x is uniformly distributed. Uniformly distributed over 0, 1. The theorem is there. Okay. Therefore, you take a random number between 0 and 1. Between 0 and 1. And then you solve that number. Using that number, you solve this equation. Suppose that number is R1. Then using quantile function, you can find this x. Let it be x1. Then again, you generate a random number between 0 and 1. Let it be R2. R1, R2, etc. are random numbers. R1, R2, etc. are random numbers. Therefore, x1, x2, etc. are random numbers. This is a simple technique. There are so many techniques available, but we will not discuss those things here. We will discuss only the simple techniques. Okay. Now, what is the policy here? You consider y is equal to f of x. Y is equal to f of x and generate a random number between 0, 1. Random number between 0 and 1. And you solve f of x is equal to r and x is equal to f inverse r. It is as simple as this. Okay. Suppose you take f of x. Actually, this is available. This is available in R base module lambda and e raised to minus lambda x. What is the distribution function f of x? F of x is probability that x less than or equal to x Therefore, this is integral 0 to x lambda into a raised to minus lambda t dt. Okay. Therefore, this is lambda into a raised to minus lambda t by minus lambda between 0 to x, lambda and lambda, between lambda and lambda. Okay. Therefore, when you substitute upper limits, minus will be coming. When you substitute lower limits, minus of minus will be coming. The 1 minus a raised to minus lambda x is a distribution function. Therefore, you take a random number between 0 and 1. Then you equate f of x is equal to r. The 1 minus e raised to minus lambda x is r. Therefore, e raised to minus lambda x is 1 minus r. You take a logarithm. Logarithm of e raised to something is that something. Therefore, it is logarithm of 1 minus r. Therefore,
Sir?
yes.
Sir?
Yes.
Sir?
Yeah, I
Yes,
can
sir,
hear.
sir, I have a doubt.
Ask
I did
me.
not get that equation. F of x is equal to lambda e raised to minus x.
This one.
Yes.
This is a density function of exponential distribution.
Okay,
F of x
sir.
is
We
equal
can
to.
take it randomly, means any distribution.
I'm explaining the procedure for this distribution.
Okay, sir. Okay, thank you, sir.
Okay. X is equal to minus 1 by lambda logarithm of 1 minus r. Suppose the first random number is r1, then you will get x1 is equal to minus 1 by lambda logarithm of 1 minus r1. Second random number you take, let it be r2. Then second random number from the exponential distribution is minus 1 by lambda logarithm of 1 minus r2, etc. Okay? So this is a technique to generate. This is a technique to generate. Okay? And one more example I will do, and I will do 1 or 2 problems in R. Suppose you take f of x. F of x is what is that? 1 by 5. 1 by 5 minus 1 less than x less than 4. It is uniform distribution over minus 1, 4. What is f of x? F of x is integral minus 1 to x fx dx. Fx dx, 1 by 5 is a constant, then t between minus 1 to x, therefore this will be x plus 1 by 5. X plus 1 by 5. Then you solve. X plus 1 by 5 is equal to r. This implies x1 is equal to 5r minus 1. Another random number, you take r2. Then x2 will be 5r2 minus 1 and so on. Now remember that this method is applicable, or this method will be very easy only when f of x is easily invertible. F of x is easily invertible. Okay? And we will go to R now. Okay. And very simple technique. Very simple technique. Okay. Suppose R1 is equal to R unif. R unif. or even if one number you take between 0 and 1. Okay, then x1 is what is the formula x1? X1 is 5r1 minus 1. 5r1 minus 1. That is, it is as simple as this. 5r1 minus 1. If you want to see r1 and x1, we have to solve them. But is R1 not found? What happens? X1 is R unif 101. That is correct. X1 is 5 into R1 minus 1. Okay, let me check. What is wrong? RM. Okay, RM is to remove all the backlog. Okay, to remove all the backlog so that is R unif 101. X1 is 5 into R1. Yeah, now it is working because something was there in some other name, or I might not have selected all the symbols. Therefore, first it is taking a random number between 0 and 1. It has taken 0.532, etc. Then, if you want to do it again, surely you will get something else. Surely you will get something else. Yeah, 0.5723145. Suppose you want to generate 100 numbers. Tell me what is the technique? Let the students tell. What is the technique? Suppose I want to generate 100 numbers using this technique. What is to be done? Hello, sir. Abdul Rafoor, sir. Please tell me. What's the technique? Other sir, tell me. Adhina, ma'am. Tell me, what's to be done? Anjali, ma'am. Ashita, ma'am. What is the technique? I am not asking to Girish. Okay. Jugida, ma'am. So, no, sorry. Jugida, sir, tell me, what is to be done? Jugida, ma'am, I think. Okay. What's to be done? Please tell me. You have to use a for loop. You have to use a for loop. Finished. You have to use a for loop. Suppose you want to do 100 numbers for I in 1 to 100. Finished. For suppose anything. If you want to do something for many times. It is foolish thing, no, to write x1, x2, x3, x4, x100. Okay, you will be getting angry with the R. Okay, first I will take the value 1, then, okay, x1 R1, print R1, print the x1. Why we want R1? No problem. Yeah. It is also quite boring, no? It is also quite boring. What is to be done? Tell me. You create a vector. You create a vector of random numbers. X is equal to, you are inviting somebody to your house. Therefore, when you invite somebody to stay in your house for some days, you have to make arrangements. Therefore, you are reserving locations to save the values of x. Okay? Then x is equal to this, r is this one, xi is 5 into r1, etc. Then this is not needed. This is not needed. That is needed only outside the loop. Okay? Suppose you want to print the x, just type x. Finished. Okay? Yeah. 100 values you are getting. 97, 98, 99, 100. These are the random numbers generated from this distribution, -1 to 4. Okay? And to generate this one, -1 by lambda, logarithm of 1 minus r. Suppose lambda is 3. Therefore, -1 by 3, logarithm of 1 minus r. Just write here, xi is equal to -1 by 3, let us put that in brackets. Whenever there is confusion, use parenthesis. That is my policy. 1 minus r1. Okay? Before that, let me clear my memory. That is RM, remove all the objects we have created so that it will not disturb you. Okay, therefore that is there. I am creating 100 locations. Then first I have to take a random value between 0 and 1. Then I use this one we have to do. First we have to find the equation for that. Then you will get values from that one. Why it is 0, -1 by 3 log non-numeric argument. What is non-numeric argument? Yeah, here what a fool I am. I am a disco fool. Okay. Logarithm of 1 minus r1. Okay. Yes. These are the 100 values. Okay. These are the 100 values. Finish. 96, 97, 98, 99, 100. You can see all the values are positive because exponential distribution is a non-negative distribution of a non-negative variable. Okay? Simple.
Sir,
Yeah.
sir, I have a doubt.
Ask me.
So in that bracket R unit,
Ah,
the first number is 1.
yeah.
Actually, what does it represent? It represents a number of
This one is
random numbers which we have to generate.
Yeah. How many numbers I want to generate?
And if I just write there 100.
Okay.
And then I got 100 numbers.
Yeah.
And then what about this for loop? I did not understand the difference.
Yeah, no problem. No. If you want to do that way, no problem. I will help you.
Both are same or both are different?
Both are different.
Okay, sir.
Both are different. In each case, it will create 100 numbers. Okay? If you are creating, that is what I told you, R is an ocean. You can generate something in different ways. Okay? Rep 0, 100. Okay, let me take Y. No problem. Y is equal to rep 0, 100. Okay? R is equal to R unif 100, 0, 1. Therefore, it will generate 100 values now. If you want to see R, you can see 100 values now. 100 values now. Yeah, it has generated 100 values. Now, x is equal to minus 1 by 3 minus 1 by 3 logarithm of 1 minus r will do. R will do. This will work. This will work. Lig will not work. No, only log will work. Only log will work. I was very careless. Yeah, I was very careless. Now, if you do it again, it will give 100 sets. 100 sets. Okay. Now, we are very cunning and we think that we are very clever. People started cheating others. They will do some blah, blah, blee, blee, blue, blue, and they will write in the paper that the result was verified using simulated values. If I am getting 100 values, 100 simulated values, you will not get those 100 simulated values if you repeat the experiment again. Therefore, there is no way for you to prove me that I am wrong. Is the point clear or not? Is the point clear or not?
Yes, sir.
Yeah. Therefore, they started a technique called pseudo random numbers. Pseudo random numbers. Okay. Pseudo means what? They are not. They are random numbers, but repeatable random numbers. Repeatable random numbers. Okay. That is to get that one. We set the seed. Set to dot to seed. Set seed. Something like 100. You can create a number. Seed means what? It is seed of a plant. If you plant a seed of jackfruit tree, you will get only jackfruit. So that this will be the seed for the generating random numbers. So that if you and me and anybody else use the same seeds, we will get same set of random numbers. So that I cannot fool you or you cannot fool anybody else. Is the technique clear or not? Set source seed, I will show you now. X is equal to
answer
set seed or answer. Otherwise, answers may be different. Because the random numbers you are getting and the random numbers your friends is getting are different. That is why they are called random numbers. But if you fix the seed fixed, then same set will be there. Now you can see 10, 0, 1, 0, 1, and x. Only 10 seconds, your doubt should be over. Yeah. 0.30. I am doing the same thing again. You see, I am getting same 10 numbers. 0.3077, 0.2561. Without that, I will do. You can see. Yeah, without seed, I am getting different. Without seed, I am getting different. These two are different. These two are same. That is when you fix the seed, okay? Nowadays, the journal people give the seed also. Okay, use this seed for simulating things. In some examinations also I have seen, you use 1, 2, 3, 4 as a seed. Okay, so that all the students will get the same answer. This is the purpose of seed. Well, seed of a mango tree or something like that. No, if you put that seed, you will get only mango tree. Okay, otherwise you may get some other tree. Set to dot to seed. Again, if you make change in the seed, you will get a different number. Suppose you are using 1, 2, 3, 4. Different than this. Here seed is 100. Instead of 100, if you use this one, you will get another set, 0.1137. But if you use same set, same seed again, no change. 1137, 1137, 6222, 6222. Okay, this is the purpose of seed. They are called pseudo random numbers. Why they are called pseudo random numbers? When we repeat the experiment again and again and again, we will get the same set of random numbers again and again and again. Yes or no?
Yes, sir.
Very good.
സർ സീഡിന്റെ ബ്രാക്കറ്റിന്റെ ഉള്ളിൽ നമ്മൾ എന്താ എഴുതുന്നത്?
സീഡിന്റെ
ബ്രാക്കറ്റിന്റെ ഉള്ളിൽ ഇപ്പം 1 2 3 4 ഒക്കെ മാറ്റി എഴുതുന്നില്ലേ, അതിൽ നമ്മൾ എന്താ എഴുതുന്നത്?
നമുക്ക് ഇഷ്ടമുള്ള നമ്പർ എഴുതാം. ഇറ്റ് ഷുഡ് ബി ഇന്റിജർ. ദാറ്റ്സ് ഓൾ. എന്ത് നമ്പർ എഴുതാം, അതിൽ നിന്നായിരിക്കും സ്റ്റാർട്ട് ചെയ്യാം. അതിൽ നിന്നായിരിക്കും സ്റ്റാർട്ട്. അപ്പോൾ എനിക്ക് ഐ നീഡ് അറ്റ്ലീസ്റ്റ് ഹാഫ് ആൻ അവർ ടു എക്സ്പ്ലെയിൻ ദാറ്റ്. How this work is happening inside the computer. Okay, starting with this, it will start. That's all. Okay, you can see some games. Okay, some games. For example, in the mobiles, you can see some games. No, പാമ്പ് ആപ്പിൾ പിടിക്കുന്ന ഗെയിം ഒക്കെ ഇല്ലേ? You can see in one trial, the apple will be in some position, then randomly it will select another position. Randomly, all those things are based on this idea. Basic idea is same. If you use any number, you can use, no problem. Any number you can use, no problem.
സർ,
Yeah.
അപ്പൊ ഈ സെറ്റ് സീഡിന്റെ ഉള്ളിൽ എഴുതുന്ന നമ്പർ നമ്മളുടെ റിസൾട്ടിനെ ഡിപ്പെൻഡ് ചെയ്യുന്നില്ല എന്നാണോ പറയണത്?
റിസൾട്ടിനെ ഡിപ്പെൻഡ് ചെയ്യില്ല.
ഓക്കെ,
റിസൾട്ടിനെ ഡിപ്പെൻഡ് ചെയ്യില്ല. പക്ഷെ എന്താ വെച്ചാല് നിങ്ങൾ ഒരു ജേണലിലേക്ക് അയച്ചു കൊടുത്താൽ നിങ്ങൾക്ക് കിട്ടിയ റിസൾട്ട് ഒക്കെ അവർക്ക് വെരിഫൈ ചെയ്യാൻ പറ്റും. കാരണം
അതൊരു കോഡ് പോലെയാണോ സർ?
അതൊരു കോഡ് തന്നെയാണ്. അതൊരു ശരിക്കും മറ്റേ അതൊരു സ്റ്റാർട്ടിംഗ് പോയിന്റ് എന്ന് വിചാരിച്ചാൽ മതി. റാൻഡം നമ്പേഴ്സ് ജനറേറ്റ് ചെയ്യാനുള്ള സ്റ്റാർട്ടിംഗ് പോയിന്റ് എന്ന് വിചാരിച്ചാൽ മതി.
Sir, may I supplement a small? Sir, depending upon the seed, we will get a sequence of a random number.
Yeah.
If we put another seed, we will get another sequence of random number.
Correct.
All these random sets of random numbers will have the same distribution.
Correct.
That is why if we do one experiment from one seed or the other seed, the ultimate experimental result would be distribution wise it would be same, but the first number would be different in one case, the second number for the second fellow it would be another one.
Yeah. That's what I told you. We may need more time to explain that concept. Okay, you plus take some books in simulation and you will get the idea. Oh no, you can get so many articles in journals otherwise, but ultimately they are distribution wise they are equivalent. So that repeatability will be there. If seed is not there, repeatability may not be there, because I don't know. Even if I use the same code, I may get different one. Therefore, I cannot verify your results. You cannot verify my results. But if you use same seed, then I can get all the results you have proved. Same values we will get. That is why they are called random numbers with an adjective, pseudo random numbers. They are random numbers, but they are not purely random numbers. Random numbers means what? No chance of repeatability. If you do this again 100 times, very rarely you will get same sequence of random numbers. Very rarely. I can say that the probability is almost zero. Very rarely. Very rarely. Because between 0 and 1, infinitely many values are there, no? Okay. This is the case for continuous distribution. But remember that this technique is useful only when the distribution function is in the nice form. The distribution function is in the nice form. For example, if the density is normal, then f of x will be integral minus infinity to x 1 by root 2 pi. Let us take simplest case, a raised to minus t square by 2 dt. This is an integral. Evaluating this integral itself is very difficult. You have to use some series expansion, etc., and do these things. Okay. This is called the inverse transformation method. Inverse transformation method. There are so many methods: accept, reject methods, okay, and method of some other functions. All right. And what about the discrete case? Discrete case, there's a problem. In the case of continuous distribution, the distribution function will be like this, between 0 and 1. Between 0 and 1. Here you are taking a number. Here you are taking a number. You are getting a unique inverse. You are getting a unique inverse. This is your action. This is a technique. Actually, this is the philosophy behind that technique. If this is a random number you are taking between 0 and 1, this is the random number you are getting. That's all. But in the case of discrete distribution, I shall show you a simple example. I don't want to waste your time. 0, 1, 2, 3. Probability something like 0.3, 0.2, 0.5, 0.4, 0.1. So that the total is 1. Then what is the distribution function? F of x is 0. When x is less than 0, it is 0.3. When 0 less than or equal to x less than 1, it is 0.5. 1 less than or equal to x less than 2, it is 0.9. For 2 less than or equal to x less than 3, this is 1 when x greater than or equal to 3. Now what will be the distribution function? Graph will be like this. Up to 0, it is 0. For 0 to 1, it is 0.3. 0.3. From 1 to 2, it is 0.5. From 2 to 3, it is 0.9. From 1 onwards, it is 1. It is a step function, staircase function. Okay, it is called a staircase function. Suppose you take a number. Suppose a random number is 0.3. All these points are inverse images. All these points are inverse images. Suppose the number is between 0.3 and 0.5. 0.3 and 0.5, okay, then you can see that probability that x is less than or equal to 3, sorry, x is less than or equal to 1, that is 0.5, and the probability that x is less than or equal to 2, less than or equal to 1 is 0.5, and the point is probability of x less than or equal to 2 is 0.9. 0.9. Okay? 0.5, 0.9. Suppose you are getting a number random number between 0.5 and 0.9. Suppose R is here. Okay? That is, R is such that probability that x less than or equal to 1 less than R less than probability that x less than or equal to 2. Probability that x less than or equal to 1 is less than r, and r is less than probability that x less than or equal to 2. Okay? In this case, we take 2 as the random number. 2 as the random number generated. Okay, this value we take. This value we take as the value of the random variable. Value of the random variable. Okay. In general, if f of xi minus 1, if f of xi minus 1 is less than r, less than or equal to f of xi, we take the random number as xi. We take the random number as xi. This is a case of binomial, Poisson, like discrete distributions. Okay, in the continuous case, you will get a unique value. Here, since it's a step function, there are infinitely many values corresponding to, it is possible, infinitely many values, okay, corresponding to a random number, which can be the inverses. I told you, corresponding to 0.3, so many values are there. Therefore, f of xi minus 1 less than r, less than or equal to f of xi, then we will take xi as the random value for the variable. Okay? I will do one example quickly. Okay? For example, let us take a known distribution. Okay? For example, probability that x is equal to x. Probability that x is equal to x is e raised to minus lambda raised to x by x factorial. Okay? For x is equal to 0, 1, 2, 3, etc. Okay? Suppose lambda is 2. Then what is probability of x is equal to 0? You know, a raised to minus lambda raised to 0 by 0 factorial. This is e raised to minus 2. Probability of x is equal to 1. This is e raised to minus 2, 2 raised to 1 by 1 factorial. That is 2 into e raised to minus 2, and probability of x is equal to 2 is 2 square. 4 into e raised to minus 2 divided by 2 factorial, that is 2 into e raised to minus 2. Okay? Therefore, we can do that in R very quickly. I shall do it for some values. What is that? You can take x is equal to 0 to 4. Okay? And px is equal to e raised to minus lambda, e raised to minus lambda into lambda raised to x lambda raised to x by x factorial. X factorial, I think factorial, it is factorial or factor?
Factorial.
Factorial, let me check. Yeah, wonderful. Factorial is working. Okay. Therefore, these are the probabilities. These are the probabilities. Okay. Now, if the random number is between, suppose the random number is point is something like then you need cumulative probability you have to find, because capital F is cumulative probability. Capital F is cumulative probability. What is the easy way to get cumulative probability? Cum sum px. For cumulative product, cum prod. Yeah, 0.1353, sum of the first two values, sum of the first three values, etc. Suppose the random number generated is 0.7212345. 0.7212345. Then that is coming between these two things. Yes or no? Therefore,
Yes,
0,
sir.
1, 2, 3. You have take the value of the random variable as 3. You have take the random variable as 3. Okay? If the random number is something like 0.222230, okay, whatever may be, it is coming here. It is coming here. Therefore, the value of x will be 1. If the random number is 0.8678904, etc., then 0.86 is coming between these two things. Then you have to take the random number as 4. The value of the variable x. Here x is a discrete valued variable. Therefore, it can take value 0, 1, 2, 3, 4, 5, 6, etc. Is it clear? Is the technique clear? If f of xi minus 1 is less than r, if the random number is between f of xi minus 1 and f of xi, we will take xi as the value of the random variable capital X. Wonderful techniques are available there. Okay, but you make thorough with this technique, and then you can refer to many techniques available in literature. You just search. Okay, that is simulation methods. Finished. Simulation methods. I am giving you all the secrets. I am not keeping anything with me, because if I die, how can I teach you? Introduction to modeling and simulation techniques, so many. Okay, don't download all those things. So many other things are there available. Modeling and simulation. Modeling and simulation. Modeling and simulation 7 this semester. Okay. It is VSSUT introduction. Yeah. Brief is 138 pages. Here you will get the answers to your doubts regarding pseudo random numbers. Brief is Monte Carlo. Monte Carlo is the name of a not name of a mathematician. It is an island. It is an island where these gambling things, etc., are conducted. Okay, advantages, disadvantages, modeling concepts, systems, etc. Okay, actually, I know only a tip of the iceberg of this technique. It's a wonderful, powerful technique, actually. And using these things, you can find the area of a curve, area under the curve like this. Okay, and you can estimate the value of pi. So many things are there. Okay, it is only you have to invest 10 hours. 10 hours. Then that will be an added advantage for these things. Self-assessment questions, reference, okay, systems, simulation and modeling, okay, system simulation. Actually, I don't know these things. I don't know these things because I have no idea about working of machines and other things. System simulation, modeling, differential equations in simulation. That's what I told you. It is a big subject. It's a big modeling differential equations. Okay. It is only one of the papers we have taken. Okay. And I think it is not a basic paper. It is not a basic paper. Computer simulation techniques, introduction to modeling and simulation techniques, introduction to modeling and simulation. I think that will be a basic paper. Okay. Yeah. One or two papers you take. This one, alpha in the xn minus 1 plus beta into model. This is the basic equation for generating random numbers, where xn is n plus first pseudo random number. Okay, random number generation. The term random number typically denotes a random variable uniform distributed in the interval 1. The term random variable, etc. Random variable commonly generated from some mechanical combination of random numbers, thus having a good mechanism for generating. True randomness is a difficult concept to define. Despite the availability of many satisfactory randomness, random number generated typically are based on deterministic formula. Using the formula, the next number of random sequence can always be predicted. That is a problem. If you are given one random number, you can predict the next random number. The most commonly used pseudo random number generators are linear, congruential, or multiple recursive, etc. So many things are there. That is all about simulation. Okay, simulation. You can take some of these notes and invest 3 or 4 hours. That is enough. That is enough. All right. Now we will check the next chapter. Next chapter is estimation. Estimation. That is also there in your syllabus, I think. Let me check whether my memory is correct or not. Statistical inference, estimation testing. Yeah, it is there. What is the purpose of estimation? What is the purpose of estimation? The purpose of estimation is starting from our ignorance of the value. That's all. We don't know things. Okay. The best example, you may not be aware of such situations. Your parents may be aware of such situations. Okay. Suppose you have to construct a house. Okay. You are now students. You don't have the experience of constructing a house. Shayan sir may be having. I know Girish is having that experience.
Yes.
What you have to do? You have to consult an engineer. You will go to an engineer, and you will explain. I want this many rooms. I want one veranda there, one veranda here, that, this, etc. And square feet, etc. And the floor should be like that. Wall should be like that. Interior decoration should be like that. My wife wants so many facilities in kitchen, etc. You will explain everything, and he will say, "You please come after 1 week." Then he will do some homework. He will calculate the cost of the material, labor cost, transportation cost, that cost, this cost, his fees, all those things. Finally, he will say, "You can complete the work in 35 lakhs." 35 lakhs. Now, this is an estimated amount for the construction of the house. Finished. That's all. That's all. Now, you will start the work maybe after 2-3 months after getting a loan. So many things are there. You have to get the permission from the panchayat or something like that. Plan approval. So many things are there. Okay. You have to get enough workers. Then you may start the work after 1 or 2 months, and the work may be completed after 6 or 7 months. And after 7 months, that means after completing all the works, you will know the exact value. Okay, sometimes it may be 37 lakhs, sometimes it may be 32 lakhs, like that. That is the actual value. This is the estimated cost. This is the estimated cost. Okay. Now you have not seen me. You don't know anything about me. You don't know about my age. What is to be done? You have to estimate my age. Shahin sir knows him. Therefore, he might have been here some years before. Okay. Now his sound is not so that very tired. Therefore, he is not 80. Okay. Something like that. You can use your experience and you will arrive at an age. Okay. That is corresponding to that may be very close to my age or something different. Again, you don't know the distance between Calicut and Delhi. You have to go to Delhi. You have to estimate the distance. Okay, you don't look at the tables, etc. Now you may ask your friends. I don't know exactly the distance, but it will take 46 hours to reach Delhi. Then you will calculate. The train will run at an average speed of 50 kilometers per hour. Therefore, it will be around 2,300 kilometers. Okay, the train fare is something like 1,200 rupees. Therefore, from that information, you can estimate the distance between Calicut and Delhi. Now, whenever we have no clear-cut idea about something, we have to estimate something. Okay, here we have a population. We have a population. We have a population. And there are some parameters involved in that population. Mu, sigma, so many things are there. We have no idea about mu. We have no idea about mu. Okay, what is to be done? Can you go to outer space and estimate? No. You have to be within the population to estimate that. You have to take some evidences. The judge can declare the judgment based on the evidences. What are the evidences? Evidences are some observations from the population. Evidences are some observations from the populations. X1, X2, etc. Xn are sample values. You can do these experiments in the campus. Unfortunately, it is Corona time. You want to find the average height of students in the campus. What is to be done? You take a list. You take a list from the administrative section or from some other sources. You take the list of all the students. Suppose there are 1,200 students in the campus. Okay, from 1,200 students, you select a sample of 100 students. What is to be done? You just take. You give numbers to the students 1, 2, 3, 4, etc. 1,200. Then sample. How many you want? How many you want? 100 students. Okay, 100 students. Then you take these 100 students as your sample observations. Yeah, 12th student you take. 12th student means the student with the number 12. The student with the number 242, the student with the number 233, student with the number 1082, student with the number 447. You measure their height. You measure their height. Okay. Then, since this is a random sample, we can easily assume that that sample is a true representative of the population. True representative of the population. Therefore, the best thing we can assume is that the sample mean is an estimator of the population. You can take another sample. You can take another sample. Okay, then you will get another sample mean, another sample mean, another sample mean. If you are very particular, you can take the mean of the means. You can take the mean of, I will explain that. Bootstrapping, I will explain. Resampling methods, I will explain maybe tomorrow or I don't know, after completing this. Resampling methods, techniques are there, which are very powerful. All those things are actually blessings of computer technology. It is very difficult to do it manually. Okay. No, this is finished. This is finished. Then can you take any value as an estimate? No, we cannot take any value as the estimate. The estimator should have some qualities. Okay, all those things are theoretical aspects. Don't worry about that. Okay, now what are the techniques? The two simple techniques are method of moments and maximum likelihood. Method of maximum likelihood. Method of moments and method of maximum likelihood. So many other methods are there. Method of minimum chi-square, modified minimum chi-square, Bayesian method. So many methods are there. I shall explain these two simple methods. We have seen what are moments. 1 by n sigma xi raised to r. This is the rth moment. This is the rth moment. The rth moment. Then you equate. Suppose there is only one parameter in the population. For example, Poisson distribution. Only one parameter is there. Only one parameter is there. Therefore, 1 by n sigma xi. This you can take as an estimator of the parameter lambda. Suppose there are two parameters, n mu sigma square. N mu sigma square. Then what is sigma square? Sigma square is expectation of x square minus expectation of x the whole square. Expectation of x square minus expectation of x the whole square. Expectation of x square minus expectation of x the whole square is equal to sigma square. Therefore, what is expectation of x square? Expectation of x square is expectation of x is mu. Therefore, sigma square plus mu square. Therefore, you can equate. There are two parameters. Therefore, you need two equations. When there are two unknowns, you need two relations. Therefore, 1 by n sigma xi. This you equate to mu. Then 1 by n. Either you can take sigma xi minus x bar the whole square or 1 by n sigma xi square. This you can equate to sigma square plus mu square. From this you can estimate sigma. It is very simple. It is very simple. Suppose there are three parameter distribution, then you need three relations. Okay? Provided these things contain the parameter. I will give you another example where these moments do not contain parameters. Next one is MLE, maximum likelihood method. That is also very simple method. I shall explain using an example. Suppose you consider the Poisson distribution. E raised to minus lambda raised to x by x factorial. Then you take random observations, x1, x2, etc., xn. These are the evidences. Then likelihood function is defined as probability that x is equal to x1 into probability that x is equal to x2, etc., probability of x is equal to xn. They are random observations. Therefore, they are independent. Therefore, this is e raised to minus lambda raised to x1 by x1 factorial, e raised to minus lambda raised to x2 by x2 factorial, etc. e raised to minus lambda raised to xn by xn factorial. Therefore, x1 factorial, x2 factorial, xn factorial, there are observations, 2, 3, 10, like that. Therefore, they are constants. Constant into a raised to minus n lambda raised to x1 plus x2 plus etc. sigma xi. This is a likelihood function. Okay? And can you select any value as lambda? It is not advisable. We have to select that value of lambda for which this likelihood function is a maximum. Use the method of calculus. That is, dl by d lambda should be equal to 0. Logarithm of it is better you work with the logarithms because they are one-on functions. Therefore, log c minus n lambda plus sigma xi log lambda. Therefore, d log L by d lambda is log c 0, derivative of x constant is 0, minus n plus sigma xi by lambda. Therefore, this is equal to 0 implies sigma xi by lambda is equal to n. Therefore, let us put a cap because he is the best one. Lambda cap is sigma xi by n. That is nothing but x bar. That is x bar, the sample mean is an estimator for the parameter lambda for a Poisson distribution. Then you have to check whether the second derivative is less than 0. Therefore, d log L by d lambda square, okay, derivative of minus n is 0, sigma xi is a constant, derivative of 1 by lambda is 1 by lambda square. Sigma xi positive, lambda square is positive, minus of that is negative. Therefore, lambda cap is equal to x bar, maximizes the likelihood function. Maximizes the likelihood function. Therefore, it is very easy. What are the observations? x1 is to xn observations. You take the sample mean. Sample mean is an estimate for the population parameter lambda. Population parameter lambda. Okay, whether it is normal, whether it is exponential, etc., this technique will do. This technique will do. But there are situations where this technique cannot be applied. Where this technique cannot be applied. I shall give you one example from that category and we will finish this discussion now. For example, you take f of x. F of x is equal to 1 by theta. 1 by theta, 0 less than x less than theta. This is uniform distribution over 0 theta. What's the likelihood function? 1 by theta, 1 by theta, 1 by theta, 1 by theta, 1 by theta n times. That is 1 by theta raised to n. Then what is logarithm of that? Minus n log theta. Minus n log theta. What is d log L by d theta? D log L by d theta is minus n by theta. This is equal to 0 implies what? Either n is equal to 0 or theta is equal to infinity. Both are unacceptable results. N is equal to 0 means what? You are taking a decision without doing anything. Sample size is 0. No observations are taking. How can we take some decision without the help of observations? Nothing. Theta infinity means what? 1 by infinity 0. F of x is 0 means what? The total integral is 0. It cannot be 1. Therefore, this is also not acceptable. This is also not acceptable. In such cases, method of maximum likelihood fails. Okay. Therefore, necessity is the mother of creation. We need some estimate for theta. What is to be done? You have the observations x1 is to xn. Arrange them according to the order. Arrange them according to the magnitude. Arrange them according to the magnitude. What is x1? Minimum of these n values. Minimum of these n values. What is x2? 2 in the brackets. This is a notation for the next minimum. What is xn? That's a maximum of x1 is to xn. And all these values are between 0 and theta because you have taken these values from 0 theta. Therefore, 0 less than x1 less than x2 less than etc. less than xn less than theta. You after arranging. Now you take L is equal to 1 by theta raised to n. This should be maximum. This is maximum when theta raised to n is minimum, because he is in the denominator. Theta raised to n is minimum when theta is minimum. When theta is minimum. Okay. What is the minimum value that theta can assume? For suppose the values are like this. Suppose theta is 5. Theta is 5. The observations are like 1 less than 2.3 less than 4.6 less than 5. 0 to theta. This is theta. Suppose you take the value of theta as 2.3. Value of the theta is 2.3. Then what is f of x? F of x is 1 by 2.3. For 0 less than x less than 2.3. In that case, what is f of 4.6? F of 4.6 is 0. Because f of x is 1 by theta. For 0 less than x less than theta is equal to 0. Otherwise, outside that range, value of the function is 0. Here 4.6 is outside 0 to 2.6. Therefore, it is 0. 2.3. Therefore, it is 0. Therefore, it will not come. Therefore, the maximum value, the minimum value that theta can assume is 4.6. If it takes a value less than that, there is no meaning for this likelihood function. There is no meaning for this likelihood function. Therefore, here the MLE of theta is maximum of the observations. Maximum of the observations. Maximum of the observations. Okay, this is a case when method of maximum likelihood fails. Method of maximum likelihood fails. We will do one problem, only one problem we will do, and we will go to okay. Okay. We will do one small example. You can also note that example. Claims in 10,000 rupees. Claims in 1,000 rupees. 1,000 rupees. Okay, it is an example I am taking from actuarial situation because I have the data with me. Claims in 1,000 rupees. 1,000 rupees on a particular policy. On a particular policy. Have the distribution with the effects two cx e raised to minus cx square. These type of distributions are very popular in physics, etc. 2cx into e raised to minus cx square. X greater than 0. X greater than 0. Okay, first let us see whether it is a PDF. Of course, when c is greater than 0, this is positive. Okay, for x greater than 0, what is integral fx? Integral fx, and I suggest you to do this using R. Okay, integrate. Integral 2c integral x e raised to minus c x square dx. What is to be done? You can take c x square is equal to u. Therefore, 2cx dx is equal to du. Therefore, this 2cx dx will be du. Therefore, integral minus u du. When x is 0, it is 0. When x is infinity, it is infinity. Therefore, this is our standard exponential. No problem. E raised to minus u by minus 1 minus 0 to infinity. E raised to minus infinity 0. E raised to 0, 1. Therefore, it is 1. Therefore, you don't worry about the total integral. Okay. Then what is to be done? 7 claims are like this. 7 claims are 1.05, 1.05, 3.38, 3.38, 3.26, 3.26, 3.22, 3.22, 2.71, 2.71, 2.37, 2.37, and 1.85. 1.85. Finds the only one parameter is there, C. Find the MLE of C. Okay, what is F? F is 2cx e raised to minus cx square. 2cx e raised to minus cx square. We have to do a little bit homework. Okay, therefore L is equal to what? 2c raised to 7. Okay, into x1, x2, etc. x7. Okay, e raised to minus c into sigma xi square. 2c x1 into e raised to minus c x1 square into 2c x2 into e raised to minus c x2 square, etc. I have taken like this. Okay, therefore all these things are, this is x1, this is x2, this is x3, this is x4, etc. Okay, therefore it is better we work with log L. 2 raised to 7, it's a constant. x1, x2, etc., x7, that is also a constant. Okay, therefore you can forget about all those things and put as a constant. Okay, plus 7 log c. 7 log c minus c into sigma xi square. C into sigma xi square. Therefore, d log L by dc is equal to 7 by c. 7 by c minus sigma xi square. Now you put this is equal to 0. This implies sigma xi square is equal to 7 by c. This implies c cap is equal to 7 by sigma xi square. Finished. You find 1.05 square, etc. You can use R. Why you go to R? You can take your calculator and find square of these things. Now you have to do one more step. D log L by dc square, that is minus 7 by c square. 7 is positive, c square is positive, therefore minus of that is negative. Therefore, likelihood function is maximum when c cap is 7 by sigma xi square. Therefore, this is the MLE of the parameter c for the distribution 2cx into e raised to minus c x square. You got some idea? I am sure that you will not get full idea, because in our degree class, we will take at least 5 hours to complete this section. Okay, starting from likelihood function, okay, and explaining these things and explaining the examples where likelihood method is failing, etc., etc. Okay, and the properties of like that's a wonderful property. Wonderful property is there that also worth mentioning. That is, if theta cap is MLE of theta, then f of theta cap is MLE of f of theta. MLE of f of theta. Okay, some conditions are there for f. Okay, continuous function, that, etc. For example, for Poisson distribution, what is the likelihood function? Likelihood function is e raised to minus n lambda, lambda raised to sigma xi divided by pi xi factorial, pi xi factorial. And we have seen that lambda cap is x bar. Lambda cap is x bar. Suppose you want to find the MLE of e raised to minus lambda. MLE of e raised to minus lambda is e raised to minus x bar. Finished. Okay, this is MLE of lambda. This is a function of lambda. For example, what is probability of x is equal to 0? Probability of x is equal to 0 is e raised to minus lambda, lambda raised to 0 by 0 factorial. It is e raised to minus lambda. Okay, you want to know what is the probability that 0 persons are infected by corona. Actually, it is not a rare event nowadays. Okay, it is a very frequent event. Okay, however, probability of x is equal to 0 is e raised to minus lambda. You want to estimate that probability. What is the probability that no child is there in a family? Nowadays, that's a trend. Nowadays, that's a trend. There is some couples don't want children because because of some reasons. Because of some reasons, they don't want any child in their family. Okay. Therefore, what is the estimate for this one? E raised to minus x bar. What is x1, x2, etc. xn here? Number of children in a family. What is x bar? Average number of children. Therefore, this is the estimate for the probability that 0 child is there in a family. Similarly, 0 defectives. Okay, 0 defectives produced by a machine. Okay, what is the probability that the machine will not produce any defective? Because if it is a machine manufactured by a good company, then number of defectives will be very less. Then they have to say, this is the probability, 0.99999 is the probability that our machine will produce 0 defectives, so that their acceptability will be very high. Any questions? Any doubts? Hello, children, ask me.
Yes, sir.
Yeah. Hello, sir.
Sir, you said that for evaluating the probability for a 0% infected with corona,
Yeah.
with that exponential, if it is 0, then naturally that would be 1. But
I didn't get your question.
sir, you put a distribution function. Can you
Okay.
show that example with the R or something, or the method to solve that?
Some response is there. Can you please type your doubt?
Okay.
You search an example for evaluating the probability of persons infected with the corona. Yeah. Yes. Can you show a simple example with R? Actually, we need additional data for that. Additional data for that. Okay?
Yes, sir.
Yeah. Additional data for that. And I will do this when we do regression. Okay? Yeah. I will do that. Then actually, I can give you another example for the time being.
Sir, your mic is muted.
Please. Please. Is it clear? Is it, can you hear me?
Yes, sir. Yes, sir.
Okay. Yeah. This I will do. Surely I will do. Okay. When we discuss regression, or when we discuss, need not be an example from corona, from something else. Okay, probability. I will estimate the probability using logistic regression. Okay. For these things, actually, we need more data. More data, actually. More data. The process is not as simple to explain in a class like this. We need more particulars. Okay. Next one is confidence interval. Confidence interval. Confidence interval. In point, the method we have discussed is called point estimation. Point estimation. Point estimation. Okay. What means this is the parameter space. In the case of lambda, lambda greater than 0. Lambda is greater than 0. Any value greater than 0 can be a value for lambda. And you are suggesting a point x bar. That is why it is called a point estimate. Point estimate. Okay, you are suggesting only one value. You are suggesting only one value. Instead of suggesting a single value, you can suggest a possible interval. Possible interval A, B, where this parameter can lie. 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 For example, suppose I ask you, what is the value, what is the price for a mobile phone? If you say it is 11,500 rupees, if you are lucky, it will be 11,000. If I am lucky, it will be 11,500 rupees. Otherwise, it will be not. And you are also not sure about the value of a price of a mobile phone. You say it will be something between 10,000 and 12,000. Rather than giving a fixed value, you are suggesting an interval, 10,000 to 12,000. Therefore, I am asking again, are you sure? Yes, 95% I am sure. That is, you are attaching a probability also to make me convinced. Okay, 5%. In 5% of cases, the value will be outside this interval. The price will be outside this interval. That means you are saying that probability that the price of the mobile phone lying between 10,000 and 12,000 rupees is 0.95. That means what? With a 95% confidence, you are telling that the price will be 10,000 and 12,000. This is what is called a 95% confidence interval. Finished. 95% confidence interval. Okay. Again, you are giving an answer. The price will be greater than 15,000. The price will be greater than 15,000. What is the special use from that information? For me, absolutely of zero use. It can be 30,000, it can be 5 lakhs, it can be 25 lakhs, it can be even 1 crore. I don't know that. I don't know that. Okay. And if you say that the value is between 10,000 and 11,000, here it is 10,000 and 12,000. The length of that interval is 2,000. Here the length of this interval is 1,000. Suppose you give me that the value is between 10,500 and 10,700 with the same level 0.95. Okay, that means what? Here the length of the interval is very small. I am getting more accurate information from the statement. Correct? I am not using any mathematical juggleries. Okay, I'm just using common sense. Okay, here the length is only 200. That is whenever the length of the interval is smaller and smaller and smaller, then the information I am getting is more dependable. I need not carry more money with me. Okay, 10,500 to 10,700 with this one. Therefore, if I carry 12,000 rupees, I can buy that mobile and come back. Okay, they are called shortest confidence interval. Shortest confidence interval. You can now imagine a number of examples. If I am asking you, what's the distance between Calicut and Delhi? You say it is between 0 kilometers and 1 lakh kilometers. It is an answer. It's an answer. You are giving an answer. That answer is correct also. But is that answer useful to me? Absolutely no use. Okay. As in Malayalam, we usually say, no, any policeman can give that answer. No, the distance between India, Calicut and Delhi is between 0 kilometers and 1 lakh kilometers. That's an answer. That answer is correct also. But that answer is of no use. Okay. Therefore, this is the concept of this one. Actually, this is a random interval. Actually, this is a random interval. You can see because you are using random samples. Now, we take a small example. Suppose X is a normally distributed random variable with the mean mu and variance 5. And you don't know mu. You have to find a confidence interval for mu. For example, 95% confidence interval. 95% confidence interval for mu. And yesterday I told you that if you have sample values x1, x2, etc., these are your evidences. Using these evidences, you have to arrive at a judgment. Okay, then X bar follows normal distribution with the mean mu, variance sigma square by n. This you can easily prove. What is X bar? X bar is x1 plus x2 plus etc. xn by n. What is expectation of X bar? that is 1 by n into expectation of x1 plus etc. expectation of xn. x1, x2, etc. xn are from normal with mean mu variance 5. Therefore, 1 by n mu 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 n times, that is mu. Therefore, expectation of x bar is mu. What is variance of x bar? They are random observations, means they are independent. Variance of ax is a square into variance of x. You prove this result. Variance of ax is a square into variance of x. Therefore, variance of x bar is 1 by n square into variance of x1 plus variance of x2 plus etc. variance of xn. That is 1 by n square into sigma square, sigma square, sigma square. That is n sigma square. Okay. Therefore, 1n you can cancel sigma square by n. That is how you are getting this result. Don't worry about the derivation. You are just applied statisticians. Okay. Therefore, you just know how to apply the result. Okay. Again, yesterday we have discussed that if x follows n mu sigma square, n mu sigma square, then x minus mu by sigma, this follows standard normal. Standard normal. Therefore, x bar minus mu by square root of this. Sigma is the standard deviation. Square root of the variance. Therefore, square root of sigma square by n, that is sigma by root n. This follows n01. N01. Again, yesterday we have seen probability that minus 1.645 less than z less than 1.645, this is 0.9. Probability that minus 1.96 less than z less than 1.96, this is 0.95. Okay, yesterday we have seen this one. Okay, even now I can show you. Okay, that is Q. You just take a Q. Okay, Q no, quantile no. Q no. Q no. Q no. 0.025, 0.1, you should get minus 1.96. Minus 1.9599, we will take minus 1.96. And it is 0.975, the other end, other tail, you should get plus 1.96. Plus 1.96. Therefore, now you have all the ingredients with you. You have all the ingredients with you. That is probability that minus 1.96 less than x bar minus mu by sigma by root n less than plus 1.96 is 0.95. You multiply by sigma by root n. What is sigma? Root of 5. Root of 5. Because n mu sigma square is 5. Sigma square is 5. Sigma by root n. Suppose you are taking 100 observations. You are taking 100 observations. Why I am taking 100? Because I can easily find root n. Therefore, it will be 10 less than x bar minus mu less than 1.96 into root 5 by 10. Okay, you subtract x bar. Probability that minus 1.9, suppose x bar is something like 40. Something like 40. Okay, into from x1 plus x2 plus etc. xn by n minus x bar minus 40 less than minus mu less than 1.96 into root 5 by root n minus 40, it is 0.95. You multiply by minus. then inequality will be changing. Okay, that is 1.96 into root 5 by 10 plus 40 greater than mu, greater than 40 minus 1.96 into root 5 by 10, into root 5 by 10. Now I don't want these things. Now I don't want these things. Okay. Then this is probability that 40 minus 1.96 into root 5 by 10 less than mu, less than 40 plus 1.96 into root 5 by 10. This is 0.95. Now you can take your calculator. 40 minus 1.96 into root 5 by 10. 40 minus 1.96 into root 5 by 10. Okay. 40 minus 1.96 into root 5 by 10. Okay. This value is 39.56. 39.56. Then 40 plus. Next value is 40 plus. 40 plus. 40 plus. That is 40.43. 39.56, 40.44. 39.56, 49.44. Okay. Probability that 39.56 less than mu less than 40.44 is 0.95. What is sample mean? 40. Sample mean is a point estimate actually. Sample mean is a point estimate for the population mean. But here you are getting an interval. There's a possibility that a probability that in 95% of the cases, the mu will be between 39.56 and 40.44. 40.44. Suppose you are getting another exponential xn, then it may be something like different because it is depending on what? It is depending on x bar. That may be something like this. 39.05 less than mu less than 40.78. That's why it's a random interval. Random interval. It will be like this. For one sample, it will be like this. For other sample, it will be like this. For other sample, it will be like this. For other sample, it will be like this. However, this mu will be here. Sometimes it may be like this. Sometimes it may be like this. 5% of the cases, the mean will be outside that. But if you take again samples again and again and again and again, okay, this interval will contain this interval x bar minus 1.96 into sigma by root 10, x bar minus of that and x bar plus of that. That interval will contain mu in 95% of the cases. Only in 5% of the these type of intervals will not contain mu. That's all. This is the method of confidence intervals. Confidence intervals. Okay. This method is called the interval estimation. Interval estimation. Okay. I prefer interval estimation than point estimation. Because in point estimation, you are suggesting only one value. Yes or no. That value may be an estimate. Okay. And if it is good, we are lucky. We are lucky. That point estimate need not be always good. Because that is based on x1 is to xn. Correct? Okay. If our method of sampling is not correct, okay, some errors are there, then the point estimate will contain more error. Point estimate will contain more error. Okay. Now you need to know this distribution. That's the important thing. x bar minus mu by sigma by root n follows normal distribution, standard normal distribution. That we should know. That we should know. Here we started with the very strong condition n mu 5. That is, variance is known. Variance is known. We have started with that strong condition. Okay, what will be the case when variance is unknown? Okay, it is 11:48 now. You may please take 12 minutes first, and we will meet at 12 o'clock. And before going for tea, if you have some doubts, please ask me and make it clear. I'm sure you will have doubts. You will have doubts because these topics are not familiar to you. You just take the concept from me now, and leisurely you can read Hogan Craig. Hogan Craig is, I told you, it is freely available. You can easily download the earlier version. That is enough for you. That itself is a very good book. That itself is a very good book. If you are after studying that one, you can go for Rohatji and Saleh. That is not that much difficult. And again, you can take wonderful notes from professors of Stanford, okay, and confidence intervals for me. Okay, you just take a PDF. That is, you need not take Lincoln University. I don't know where it is. And estimation and confidence, chapter 9 confidence, statistical estimation. Okay, and also the lecture notes by IGNO. Lecture notes by IGNO. Consider distribution of serum cholesterol levels for all males in US who are hypertensive and who smoke. The distribution has an unknown mean mu and standard deviation 40. This is what I'm not convinced. Mean is not known, but standard deviation is unknown. That was a confusing thing for me for a long time. Then after a long time only, I realized that this can be estimated using some pilot study. Okay, suppose we draw a random sample of 12 individuals from population and find the mean cholesterol is this. Okay, and sampling weight is important to consider interval estimate mu. Okay, they are not going for point estimation. They got this one 191 for 243. Okay, for that population, the 95%, 99% confidence interval is 183 to 51, like that. X bar, this is what we have done now. X bar minus 1.966 sigma by root n less than or equal to mu, etc. Okay. Confidence, what do you mean? In repeated sampling from normally distributed population with a non-standard 101 minus interval of this one will in the long run cover the population. That is the meaning. In the long run. See the simulations in R. Okay. And you can simulate that in R. And you will get the diagrams I have shown before. This is what I am going to discuss after the tea break. Sigma is unknown. Sigma is unknown. Okay? Sigma is unknown. And you can simulate this in R. What is to be done? What is to be done? Tell me. The technique you tell me. Technique you tell me. What is to be done to simulate this type of intervals? You simulate random observations x1, x2, etc., xn from the population, that is all. You know how to simulate observations from normal distribution. What is the distribution here? Normal with the mean, mu, and this one is the confidence interval. This one is the confidence interval. Okay, and you generate random observations x1, x2, etc., xn, and for each set of same size, 50 observations or 100 observations, you generate, and for each set you generate this interval. Okay, and you see how many such intervals are. containing this mu or not, like that. Right. Okay. This is a wonderful study material. Wonderful study material. It gives very simple examples, and very easy examples. Very easy example. And if you look at the notes of the same author, see the simulations. That means he might have done some simulation somewhere. Who is that author? J. Huang. Okay, J. Huang. You take the notes of that professor. Surely that note will give you more ideas. And once you complete that one, you can have the basics idea. Okay, the basics. These are things actually we have done now. Yeah, this is what I have shown you. Tick, 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 tick. This one is not containing. The interval misses the mu. Okay, and this can happen maximum in 5%. The others all captures mu. Okay, this is a way of learning, no? You get some idea from somebody. My battery is running low. What happened? I don't know. Yeah, I have not switched on my. Yeah. These are very simple notes. Very simple notes. Using the random number generator at this one. Yeah, you are generating these numbers. We get the following data. And they are doing confidence intervals. What is the practical question that requires estimating parameter? Identify the parameter and they choose a level of confidence, etc. It is only 9 pages. This is an important question that I will discuss. What is appropriate sample size? What is appropriate sample space? Okay, for your study, you are doing some experiments and using the information, you have to estimate how many data I have taken. In this case, they have done one example. Therefore, approximate sample size is 15. Okay, like that. I shall give you this link to you. This link to you. This link also I can give. Oh, and where is the other one? Oh, I have not saved it, I think. Yeah, you can take this. I am sure. Now youngsters are very experts in computer techniques. Confidence for mean and difference of means. Mathematics article. Okay. Yeah, they are giving advanced examples. They are giving advanced examples. No need not go for this in the beginning. It is better you go through these things. Okay. Okay. Oh, now it is already 11:56. Okay, you take 10 minutes rest and we will meet at 12:06.
Okay, sir. Thank you very much.